everyone, I'm Dr. Rizwana, working as a professor of physics in Institute of Aeronautical Engineering. Today we are going to derive equation of motion for matter waves. So we know what are matter waves. So de Broglie, he has given this hypothesis. According to de Broglie's hypothesis, we know that just like light radiation, we know that light radiation, it will exhibit dual property. So it will exhibit both particle nature and wave nature. So it has got dual nature, both it will exhibit properties of wave and particles. So according to de Broglie hypothesis, just like light radiation, uh, even material particles, all the fundamental material particles like electrons, protons and neutrons, if we take those material particles, they are also going to have dual nature. So we know that suppose if I take electron, so electron obviously it will exhibit particle nature, but this electron, it has this property of exhibiting even wave property. So even these electrons, like material particles like electron, protons and neutrons, they can exhibit both wave and particle nature. They can also have this wave particle duality. So that concept, it is given by de Broglie's hypothesis. So according to him, so in nature everything should be symmetric. If light radiation can have dual characteristic, then even fundamental material particles should also have dual characteristic. And according to him, if we make material particle move, if we take moving material particle, then it will behave as a wave. So a wave associated with a moving material particle is nothing but matter wave. So when we have material particle behaving as a wave, when it is accelerated or when it is made to move, then in order to explain its wave motion, there should be one wave equation. So today we are going to get that wave equation associated with matter waves. So when material particle moves, according to de Broglie's, it will behave as a wave, and that wave equation related to matter wave, that particular wave equation we are going to derive it. And here today we are going to focus only on time independent wave equation. So we are not going to focus on time dependent, just we are going to get equation which is independent of time. And of course this equation was done by scientist Schrodinger, so that's why this equation, it is also called as Schrodinger's wave equation of matter wave. So for that, in order to derive this wave equation, we are going to consider wave function. So as you can see that suppose if we have a particle whose mass is m and velocity is v, then in order to take its wave motion, we are going to get it in terms of its wave displacement. So here I am defining displacement of wave, or simply it is called as wave displacement, and it is given using this particular notation psi. This psi, first it will represent displacement of a wave. So if we have a particle moving with certain velocity, then it will exhibit property of a wave, and this comes according to de Broglie's hypothesis. And this particular wave displacement, it is given by particular notation psi. And we say that this psi, it also represents wave function of the particle. So next, after we get the equation for this matter wave, we are going to discuss in detail what exactly is this wave function associated with material particle. But for the time being, we are saying that when we have a wave, then with that wave, we have one wave function that will describe behavior of the particle, and it is represented by this notation psi. And we know that generally, now we are going to take help of wave functions that are defined for progressive waves. So by taking that wave function associated with progressive waves, we are going to get the equation for matter waves. And we know that wave function associated with progressive wave, it is given by this particular waveform. And if you see this particular expression, it consists of two terms. First term is sin naught, this is our first term, and our second term is sine omega t minus kx. Generally, when we talk about wave functions associated with of course, material particles. So if you talk about progressive waves or stationary waves, generally their wave displacements, they are represented in terms of either sine, cos or exponential, because we take these wave functions to be periodic. And always periodic functions, they are represented by sine, cos or exponential. And in this case, we have defined this wave function in terms of sine. And as I told you, here we have two terms. First term, psi naught, it is, if you take this psi naught, it is called as amplitude. So, and here this psi naught wave function, it is expressed in terms of this coordinate x and also with respect to time t. And then coming to this second term, it is given in terms of angular frequency, and of course what is k here? K, it is called as propagation vector. So k is propagation vector, and it is also called as wave number. And how it is given? It is given as k is equal to 2 pi by lambda. So using this representation of wave function associated with progressive waves, we are going to derive equation of motion of matter waves. Now what I am going to do, I am going to differentiate this particular expression for wave function with respect to time t. And here if you take this, here in this case, of course our wave function, here it is function of both time and position coordinate. But when we take this particular psi naught, which is called as amplitude, it is function of only coordinates. It is independent of time. So it is not dependent on time. It is function of only coordinates. So that's why when we differentiate here, if we take differentiate with respect to x, so here we'll find psi naught to be a constant, and then our sine omega t minus kx, it becomes cos omega t minus kx. And here of course if we take, because we are differentiating with respect to x, here we'll have minus k. So finally we'll have minus k sine naught cos omega t minus kx. And here sine naught is nothing but a constant, because we are taking it as amplitude. Now we are differentiating again with respect to x. So then we have our dou square psi by dou x square. Now why we are using partial differentiation here? Because our wave function psi, it is dependent on more than one variable. So here in this case, it is dependent on x coordinate, also it is dependent on time. So if you have your wave function dependent on more than one variable, then we'll make use of partial differentiation. And here in this case, we are considering one-dimensional motion. If we consider three-dimensional motion, then here again your wave function, it will be a function of x, y and z coordinates. So if we differentiate again this particular function with respect to x, then we end up having it as minus k square sine naught sine omega t minus kx. And here of course k is our propagation vector, and also it is called as wave number. And we know that the sine naught sine omega t minus kx is nothing but our wave function, which is defined for progressive wave, and it is given as minus k square psi. I am taking this minus k square psi to the other side, then minus will become plus. After that, in this particular equation, so from this equation we are going to move further, and as you can see, this propagation vector k, it is given as 2 pi by lambda, right? And if I substitute this k value here in this equation 2, in place of k square, I'll have 4 pi square by lambda square. Now this is differential form of classical wave equation. So this is our general classical wave equation, differential classical wave equation. Now at this point, I'm going to apply de Broglie hypothesis. So what is our de Broglie hypothesis? See, all this we have done for progressive wave. Now, what we are going to do? So according to de Broglie hypothesis, here comes the concept of matter wave. What is matter wave? Having dual nature of both particle and wave. So what we are going to do, we are going to take expression for de Broglie wavelength, which is derived using de Broglie hypothesis of dual nature of material particle. And according to de Broglie hypothesis, what is the de Broglie wavelength? De Broglie wavelength, it is given by h by mv. Lambda is wavelength associated with matter wave. Whereas in denominator we have m and v. M is mass and v is velocity of material particle. So left hand side it is parameter related to matter wave, whereas right hand side if you take it is a parameter related to material particle. So if I substitute this value of wavelength here, then I end up having it as 2 square psi by dou x square plus 4 pi square m square v square by h square psi is equal to 0. Now, we know that total, if we take a particle, if its total energy is given as E, we know that total energy it is given in terms of kinetic energy and potential energy. So, K is our kinetic energy and V is potential energy. And we know that generally kinetic energy it is expressed as half mv square. Okay, so therefore our total energy will be half mv square plus v, and if I take this potential energy onto the other side, then I have my kinetic energy as total energy minus potential energy. Then dividing numerator and denominator with m, then I have my numerator as m square v square. In the denominator we have 2m, and I have taken this 2m to the other side, then we have 2m into e minus v. If I substitute this value in our equation 4, then finally we have this equation rho square psi by dou x square plus 8 pi square m e minus v by h square psi is equal to 0. So this is one form of Schrodinger's time independent wave equation for matter waves. So here we can simplify this equation further, because in quantum mechanics we'll be using frequently this value h by 2 pi. So we'll try to simplify our wave equations by replacing this h by 2 pi factor as h cross. So what is our h cross? H cross is h by 2 pi, and in our previous equation if I replace h by 2 pi by h cross, then I end up having my simplified Schrodinger's wave equation as dou square psi by dou x square plus 2m into e minus v by h cross square psi is equal to 0. So this is one-dimensional Schrodinger's time independent wave equation. If you want to extend this wave equation to three-dimensional wave, we have considered one-dimensional wave in the beginning for simplicity's sake. But once we get one-dimensional wave equation, we can extend it to three-dimensional wave equation. So for that, what I have to do, in place of dou square psi by dou x square, I have to introduce operator del. So you must, so we know that Laplacian operator del square, how it is given? It is given as dou square by dou x square plus dou square by dou y square plus dou square by dou z square. So in place of this, dou square psi by dou x square, I am going to introduce this dou square psi by dou x square plus dou square psi by dou y square, dou square psi by dou z square. Now here in this case, wave function it is dependent on three coordinates. What are those three coordinates? X, Y, Z coordinates. So this is three-dimensional time independent wave equation, Schrodinger's wave equation, which is independent of time. We have removed time factor, and if you want to write that equation in simplified way, so what we'll do, we'll replace this with Laplacian operator del square, then final simplified time independent Schrodinger's wave equation for matter wave, it is given as del square psi plus 2m into e minus v divided by h cross square psi is equal to 0. Now in this, we have our m as mass of material particle in motion, which is giving rise to matter wave, and E is total energy associated with material particle, V is potential energy of material particle, and of course h cross, it is h by 2 pi. And here in this case, our wave function site is dependent on position coordinates x, y, z. Here it is not dependent on time, because we have removed time factor. We have made it dependent only on position coordinates. So this is our simplified wave equation, Schrodinger's wave equation. So in this session, we got one wave equation for matter wave, and here this wave equation is dependent only on position coordinates and it is independent of time. Thank you. I'll end my session here.
Like, share and subscribe. Hit the bell icon for more updates.